In the previous section, we dealt with classifying of real numbers, which is really getting at understanding what the real numbers are and the different subcategories within that of being rational and irrational, integers, whole numbers, natural numbers, etc. Really just understanding the numbers themselves. Now, ultimately, of course, we want to be able to do math, do things with the numbers, right, as we get into algebra. And we're going to get to that by the end of this section in simplifying expressions. Now, the thing is that we oftentimes do math, but we don't really think about the actual steps we're doing. We just kind of know it's true a lot of the times. And what we're going to really dig into here today is giving a rigorous, justified reasoning to why we're able to take all of the tiny steps that we do to be able to simplify expressions. That comes down to understanding the properties of real numbers, things that we know are true for all real numbers, and we're going to break those apart just now. Now, before we go through these properties of real numbers, I want us to understand that we really can get by in math if we only had 2 operations rather than 4. When I say operations, I'm referring to addition, subtraction, multiplication, and division. Those are the 4 main operations that we usually do in math, right? But we can get by if we just restrict ourselves to 2 of those operations. The first of which is addition, and the second of which is multiplication. And we'll kind of explain this later on. So we're excluding subtraction and division. It's because subtraction really is just kind of a special form of addition. So we can define subtraction based off of addition existing. And then similarly, we can also define division based off of multiplication existing, because division is just a special form of multiplication. So we're going to talk about different types of properties of real numbers. In the first column, I'll give the actual name of the property that will illustrate through example. And then I just have some kind of pictures there that I'll use to help explain why some of the names of these properties, might make sense. All right, so for the first property right here, what this property says is if we're dealing with an addition property, first of all, then we're going to have to be using the operation of addition, of course. So what the addition version of this property is going to say is that if I take a real number and another real number and I add them together with each other, it's going to equal always another real number. It won't equal a number that's not a real number. Okay, and that seems pretty logical, right? It turns out that the same thing is true in multiplication as well, that if you take a real number and another real number, you're going to get another real number when the operation you perform with the 2 original numbers is multiplication. Okay, so for examples, concretely, actually using numbers for these, I don't know, if you take negative 3.2 and then you add 1.7 to it. So there you can see we're doing that operation of addition with the 2 numbers. You're going to get negative 1.5. So a real number and a real number, right? They're both real numbers. And our answer that we got, negative 1.5, is also a real number. So that's just an example. It just turns out that it's always going to be true. And then if you did, I don't know, 2/3 times 5/7, multiplying 2 real numbers, you're going to get 10/21, right? So there's an example there. I haven't named this property yet. The name of this property that I'll give to you now it's called the closure property of, and then after that word of, you could either fill in the word addition or multiplication, depending on whether you're using the operation of addition or multiplication. The reason why closure makes sense is, I'll use this box to kind of help explain that, is if I take a real number that's located, pretend it's in the box, and then maybe it'd be better if I actually drew something in the box. There, that makes it look like it's more in the box, right? So if I pick a number in the box and I pick another number in the box, so I pick 2 numbers, and let's say I add them together, okay, it'd be really silly if my answer was a number outside of that box, because you're not going to get a number that's not real. So closure just means if you take any 2 things from within a set and you perform an operation, you're going to get another member of that set if it's closed. If it's not closed, then you'd get a number outside of the box or outside of the set. But it just turns out that, yeah, real numbers are closed under addition and multiplication. So that's the closure property. Another thing that's true in math, which you have a good intuition of understanding, I'll just give some examples. We know that like 2 plus 8 does always give you the same answer as 8 plus 2, doesn't it? Okay, and that works for any numbers that you choose. Like if you did pi plus the square root of 2, then the square root of 2 plus pi is going to give you the same answer. Okay, so for adding numbers, it works when you reverse it. Subtracting, if you think about it, I'll write that off to the side. Like if you did 1 minus 3, that gives you an answer of negative 2, right? And then if you did 3 minus 1, that gives you an answer of positive 2. So you don't get the same answer if you reverse the order of those elements in subtracting, right? So you get different answers when you're subtracting. So that kind of makes addition a little bit more special in that way, right? Same thing works for multiplication. So if you did, I don't know, like 3 times negative 5, then that's going to be the same thing as negative 5 first and then times by 3 because they're both equal to negative 15, right? So in general, this would just be kind of saying that if you take any number, let's say a and b, then it's just the same thing when you do b and then a when you're adding the numbers together with each other, or if you are multiplying the numbers together with each other, right? The name that we give this property is kind of like this right here. So like oftentimes you have to go from home and then you go to work or you go to school and then you go back from work or school and you go back to home at the end of the day, right? So a lot of times people refer to that as their commute to their places, right? So a commute, you commute there and then you commute back, so it goes forwards and backwards. So just kind of like you see here how you can reverse the order and it's the same both ways. That's why we give this property its name the commutative property, because it's like kind of like commuting, right? All right, and then for a third property, this property is really important in that you have to keep the numbers in the same order. So like if I did 4 and then 7 and then negative 5, let's say, then I'm going to have to write the numbers in the same order, 4, 7, and negative 5. And because I put this in the addition column, I'm going to add all 3 of these numbers together with each other. And we're going to get equality on both sides here. It turns out that if I were to do 4 plus 7 first and then add the negative 5, versus if I did 7 plus negative 5 first and then I add the 4 with the result of that, you're always going to get the same thing. So I'm just kind of changing which numbers I add together first, just kind of changing the grouping symbols. It always works out because really this becomes an 11 plus negative 5 problem. Think about it, right? 4 plus 7. And then the other problem becomes a 4 plus 2 problem because 7 plus negative 5 is 2. But on either side, 11 plus negative 5 is 6 and 4 plus 2 is 6. So you're always going to get the same answer in those cases. Same thing would be true in multiplication, that if you did like 2 times 5 times 1, and then you did 2 times 5 times 1, and then you were to, I don't know, group those 2 numbers together first, and then group those 2 numbers together first, like you're always going to get the same answer no matter what. So in general, I don't know, let's call them X, Y, Z. I guess I should space those out if this side is the addition side, right? These ones I can put closer together because we're just multiplying. Okay, so if I were to do like x plus y plus z, and I added y and z together first, and then it added x, it makes no difference if I do x plus y first and then add z, like that's the same thing. And then for multiplication, like you can do x times y and then times z, or you could do y times z and then do the x times that, and you get the same answer. This property is called the associative property of either addition or of multiplication. So associativity is always going to involve at least 3 elements there, and really you're just changing the grouping but keep in mind that those elements have to stay in the same order on both sides, because otherwise if you're changing element order, that's really dealing with commutativity. Okay, just a couple more properties on this first little table right here that we want to highlight here. The goal of the next property, you see I have a picture of a mirror here, is that like when you look in a mirror, you see yourself. So what we want to try to do here is to preserve our identity, or to keep ourselves the same through these operations of addition and of multiplication. So I'll pose a problem to you right here. I don't know, just pick a number, -7. So because this is an addition property, I'm going to add something, but what should I add in that blank right there so that when I look in the mirror, I still see myself, so I still see -7. And the answer to that, of course, is going to have to be the number 0, right? So it turns out that we can generalize this to say that if I don't know, pick a number m, let's say, that if you take m and you add the number 0 to the number m, that's always going to make it equal to the same number m that you started with, right? So if we turn this into the multiplication version of this property, like if we were to start with the number m, but now we were to multiply, what would you have to multiply m by to make it equal to the same number m? It's not 0, right? It actually has to be the number 1. So we use a different number when we're multiplying. An example of that would be if you did, 1/2 times 1, you're still going to get 1/2, of course, right? This is called the identity property. Okay, pretty easy name to hopefully recognize what that means, because identity means you want to maintain your identity, keep it identical, so whatever number you start with, you keep it identical. So you either add a 0 and it stays the same, or you multiply by 1 and it stays the same, right? The last property is going to use, let me change the color of that one there, trying to put that in orange, there we go. So the last property here is related to the identity property in that it's really centered around either the zeros or the ones. So the thing is here is that I'm just going to pick a number like, I don't know, 3. So if I were to do 3 and I were to add something to 3, I actually want to make it equal to 0. And then similarly, with the example that I'll use here, I'll take 3 and I'm going to multiply it by something, and I want to make it equal to 1. Okay, so 0 when we're adding, and 1 when we're multiplying. I think my picture's in the way there. There we go. So if we were to try to fill in these blanks, if we start with the first one right here, 3 plus 1 is going to equal 0. The answer to that, of course, is going to be -3. And so in order for us to always get this to be accomplished, in other words, for us to always equal 0 from taking two numbers and adding them together, that basically means that if I start with some number, let's say n, the other number's got to be negative of n, right? Or in other words, the opposite of the number. So if we're adding opposites, we're going to get that answer there, 0. So basically what's happening here is we're canceling, kind of a loosely use of terms there, canceling the numbers out. Then if we go to this other example over here, 3 times something is equal to 1, the answer to what this number right here should be is it should be 1/3. Some other examples like here might be if I had, let's say, 7/4. If I were to times 7/4 by something to equal 1, the answer would have to be 4/7. Okay, so it turns out that these two numbers that have to pair with each other to multiply and equal 1, they have to be what we call reciprocals, right? You're flipping the numerator and the denominator around. So what we could say about that then is if we have some number n, its reciprocal is always 1/n. And if you think about why that's true, like if n were 4, then 1/n would be 1/4. And it works for fractions too. So if n was 2/3, then you'd be multiplying by 1/n, which would be 1/2/3. But then right there, right, if you're like dividing by a fraction, like you could do like keep change flip or same change flip, however you want to phrase that, right? And so you're basically just kind of now actually multiplying by 3/2. Again, my my picture is covering that up. And so then there, that's actually the reciprocal, right? So yeah, that's how we can kind of phrase that as n times 1 over n. That's going to be equal to the value of 1. So I haven't very clearly explained quite yet what's going on in this last property that we just highlighted. Really what's going on in these examples here is you're canceling out the number you started with and bringing it to this number 0 or this number 1, depending on whether we're dealing with addition or with multiplication. So the name that this property is given is actually, it's a great name, the inverse property. Kind of sounds like reverse, right? So it's like, you know, these two numbers reverse each other when you add them, and these two numbers reverse each other when you multiply them with one another. Now, I want to give some good terminology to just a couple of these numbers that we just highlighted right here. So this number 0 right here, the number 0 is oftentimes referred to as the additive identity, because whenever you add a number with this additive identity, it keeps the identity of the number that you're adding 0 with. So similarly, this number 1 is also called an identity, because anytime you multiply with 1, you preserve the identity of that number you're multiplying 1 with. But it's the identity under multiplication, not under addition, because if you add with 1, you change your answer, right? So it's called the multiplicative identity. So you can use that in the identity property, and it just turns out that in the inverse properties that you're going to get either the additive identity or the multiplicative identity as your answers. A couple more properties down here that we just want to highlight. Very simple. I'll just abbreviate right here. We have something that's called the multiplication property. I guess I should write that word property. Multiplication property of 0. And basically all the multiplication property of 0 says is that if you pick a number, let's say x, and you clearly multiply with 0, what's your answer going to equal? Well, anything times 0 is going to equal 0, right? So for example, I don't know, you take 479 and you times it with 0, you're going to get not 479, you're going to get 0. That would be if you're timesing by 1. All right, and then if we were to do the multiplication property of negative 1. Very clearly, that name tells you exactly what's going on. So if you pick a number x and you times it with negative 1, what's it going to equal? It's going to equal negative x. So, for example, if I took like negative 4 and then I times it with negative 1, it's supposed to be equal to negative of the number I started with, which is negative of negative 4, and negative of negative 4 is equal to positive 4, of course, right? Excellent. Okay, and then I would just want to highlight here one other property. So this property right here, it's called the distributive property. And you're very familiar with this, I'm sure. The distributive property, just by example, of course, is like if you have 3 times x and then you have 5x plus 9, let's say. Okay, that 3x is going to be able to multiply to each of the terms inside of that parentheses there. So this is going to be equal to 3x times 5x is 15, and then x times x, which is written as x squared. And then we can also multiply the 3x to the 9. So then we get plus 3x times 9 is plus 27x. So that's a concrete example of a distributive property. More generally, if you take any sort of element and then you multiply it to a sum of 2 elements, it's going to be equal to that a times b and then plus the a times this c. So it's just kind of the multiplication distributes throughout that sum.